I can recite the speed of light on command. 299,792,458 meters per second. Rattle it off at a dinner party, and you'll sound smart doing it. But here's what I never did. Not once, in all the years I knew that number. I never asked why light got the credit. Out of everything in this universe, why did we name the ultimate cosmic speed limit after a beam of light hitting your eye? I only started asking because of one fact that stopped me cold. In 1983, a room full of scientists sat down and quietly stopped measuring the speed of light. Forever. Not because they'd run out of better instruments. Not because the number was already perfect. They simply declared it fixed, locked it in place, and walked away from it for good. Read that again, because it sounds backwards. We didn't get more precise about the speed of light. We stopped caring what its exact value was, and started using it as a ruler instead. That one decision is the loose thread I want to pull on. Because once you pull it, the whole idea of a speed of light comes apart in your hands. And something stranger, and far more useful, is waiting underneath it. By the end of this, you'll see that the number you memorized in school was never really about light at all. Light just happened to be the first thing we caught running at it. To understand how we got the name wrong, you have to go back to 1676. To Paris. To a Danish astronomer named Ole Rømer, staring up at one of Jupiter's moons, night after night, doing the most tedious job in astronomy. He was timing eclipses. Io, one of Jupiter's 4 largest moons, slips in and out of Jupiter's shadow like clockwork, roughly every 42 hours, and astronomers used those eclipses as a kind of cosmic stopwatch. Rømer's job was simply to log the times. Except the times wouldn't behave. When Earth sat closest to Jupiter, the eclipses ran early. When Earth swung around to the far side of its orbit, months later, they ran late. By as much as 22 minutes. Every other astronomer chalked it up to error, a flaw in the tables, something wrong with the measurement. Rømer didn't buy it. He noticed the delay tracked something specific, exactly how much farther Earth had to be from Jupiter at any given moment. And that gave him an answer so simple, it's almost embarrassing that no one had said it first. Light is an instant. It takes time to cross a distance. That 22-minute drift wasn't Io misbehaving. It was light, crawling across the extra width of Earth's orbit. For the first time in human history, someone had caught light in the act of arriving late. Here's the part almost nobody tells you, though. When Rømer stood up in front of the Paris Academy in 1676 and said this out loud, it did not go well. The observatory's own director, Giovanni Cassini, had seen the exact same drift in the data years earlier. He'd looked right at the evidence and talked himself out of it, blaming Io, blaming the tables, blaming anything except the one explanation staring him in the face. It took a Dutch physicist, Christian Huygens, who never touched a telescope for this and worked purely off Rømer's numbers, to take the claim seriously enough to publish it. Hold on to that, because it's going to matter later. The data never announces its own meaning. Somebody has to be willing to believe the pattern over the comfortable explanation. For the next 200 years, that was basically the whole story. Light was fast. Faster than anything else humans could catch. Spinning mirrors, rotating gears, one clever mechanical trick after another, each one shaving the number closer and closer to the truth. Generation after generation of physicists treated it the same way you treat any other stubborn number in nature. Something to be pinned down more precisely, decimal by decimal, with a better clock or a longer baseline or a faster spinning wheel. Nobody was asking why the number existed. They were just racing to measure it better than the last person had. Light was simply the fastest thing anyone had ever caught red-handed. Then the twist arrived, and it didn't come from anyone studying light at all. In the 1860s, a Scottish physicist named James Clerk Maxwell was buried in a completely different problem: electricity and magnetism. He was tidying up 4 equations describing how electric and magnetic fields behave, And hidden inside that math was something nobody expected. A wave. A ripple that electric and magnetic fields could build entirely out of empty space by continuously recreating each other. Naturally, Maxwell wanted to know one thing. How fast does it move? The answer his own equations handed him was built from two numbers that had nothing to do with light whatsoever. One came from experiments with charged objects, how hard two charges shove each other apart. The other came from coils and magnets, how strongly a current generates a magnetic field. No lamp involved. No glow. You could run both experiments in a pitch-black room with nothing but batteries and wire. Maxwell multiplied the two together the right way, and a speed fell out. Roughly 300,000 kilometers per second. And that's the moment Maxwell froze. Because he recognized that number. Everyone did. It was the speed of light, the same one astronomers had already clocked with moons and mirrors and spinning gears. Sit with how strange that actually is. A calculation built entirely out of static electricity and bar magnets spat out the exact speed light had been measured at, using completely different tools, in a completely different field, for completely different reasons. There's only one honest way to read a coincidence that precise. Light must be an electromagnetic wave. Maxwell said so. He was right. But here's the detail that changes everything. The hinge this whole video swings on. That number didn't come from light. It came from two properties of empty space itself. How strongly a vacuum reacts to electric charge. How strongly it reacts to a moving current. Properties of the room, not of anything sitting inside it. We'd measured the room and named the number after the first tenant we happened to see moving through it. Nobody realized it at the time, least of all Maxwell. He wasn't trying to explain light. He was trying to fix electricity and magnetism. Light being an electromagnetic wave was a bonus he stumbled into on the way to somewhere else entirely, which makes what came next even stranger, because the deeper implication of that discovery sat quietly unnoticed for decades. Which brings us back to 1983, and that strange decision I opened with. For 3 centuries after Rømer, physicists kept sharpening their instruments, chasing a more precise value for the speed of light. But something odd kept happening. The better their tools got, the less they were learning about light, and the more they were bumping into the limits of their own rulers. Here's the problem. Back then, a meter was defined by an actual metal bar, locked in a vault in France. Every measurement of light speed was secretly just a measurement of how many bar lengths light covered per second, and that bar had its own tiny uncertainty baked in. Metal expands. Metal contracts. It was never going to be precise enough for what physicists needed. So in 1983, the people in charge of the world's units did something almost sneaky. Special relativity had already proven, again and again, that light's speed in a vacuum is the same for absolutely everyone, no matter how fast they're moving. So they flipped the whole relationship on its head. They declared the speed of light exactly 299,792,458 meters per second, permanently, by definition, with zero uncertainty ever again. Then they redefined the meter itself as whatever distance light travels in 299,792,458th of a second. Sit with what that actually means. We stopped using our ruler to measure light. We started using light to build our ruler. Every time a modern lab clocks how far light travels, they're not discovering anything new about light. They're calibrating their own equipment against a number that was never in question again. That is not how you treat a fact about light. That's how you treat a conversion rate. The kind of fixed exchange number you'd use to turn inches into centimeters. We just handed it a much bigger job. So if the number was never really about light, what is it actually measuring? This is the one idea I'd keep if I had to throw away everything else in this video. Because once it clicks, relativity stops being a pile of bizarre facts you memorize, one after another, with no visible connection between them, and becomes one single picture you can hold in your head for the rest of your life. Every strange result physicists have ever measured about time, moving clocks, twins aging differently, particles outliving their own lifespans, falls out of this one idea automatically. You won't need to memorize the results anymore. You'll be able to derive them on the spot. Picture this. Every single thing in the universe, you, me, a rock, a photon, is handed an identical, fixed budget of motion the moment it comes into existence. Think of it as a pie. Always exactly the same size, no matter who owns it. And that pie only has two slices. One slice is motion through space, how fast you're covering distance. The other is motion through time, how fast you're aging, ticking forward, moving from one moment into the next. You cannot shrink the pie. You cannot grow it. The only freedom you get, the only choice in the entire universe, is how it gets sliced. Here's the twist most people never see coming. Sit perfectly still in your chair right now, and you are not motionless. You're spending your entire pie on the time slice. 0% toward space, 100% toward time, which means you are aging at the fastest possible rate a human being can age. Stillness isn't the absence of motion. It's motion, fully redirected into time. Now stand up. Walk across the room. You've just shaved a sliver off your time slice and handed it to space. The pie hasn't grown. You've only reallocated it. And because the total is fixed, whatever you spend on space comes directly out of time. You are, quite literally, aging microscopically slower than if you'd stayed in the chair. Too small for any clock on Earth to catch. But not zero. It's real. Push it further. Get in a jet. Get in a rocket. Get close to the universal limit, and you're shoveling more and more of your pie into the space slice. Your personal clock keeps slowing relative to anyone who stayed still. Nothing is reaching out to sabotage your watch. There's no invisible hand. You're simply spending a bigger share of a fixed budget on space, which leaves less for time. That's the entire mechanism behind time dilation. Not mysticism. A pie and a choice. And the trade isn't gentle. It isn't linear. At 10% of the limit, your time slice has barely moved, buried past any decimal a human could ever notice. At 90%, it's dropped by more than half. Push past 99, and it collapses to a sliver, a fraction of a fraction. The closer you creep towards spending the whole pie on space, the more violently expensive every extra percentage point becomes. That's why your entire life feels like nothing is trading at all. Walking, driving, flying, you're haggling over the last few decimal places of a pie that's already 99.99% committed to time. You'd need real speed, a meaningful fraction of the limit, before the negotiation gets loud enough to hear. And this same budget explains why nothing can outrun the limit. You cannot spend more than 100% of a pie. Once your whole budget points toward space, there's nothing left in the time slice to rate. The speed limit was never a wall you slam into. It's simply what 100% looks like. Here's the part that should stop you. This isn't a thought experiment dressed up to sound clever. It's been measured. Deliberately. On purpose. With machines built specifically to catch it happening. In 1971, two physicists, Joseph Hafele and Richard Keating, did something wonderfully direct. They loaded 4 cesium atomic clocks, the most precise timekeeping devices on Earth, onto commercial airliners and flew them around the entire planet, once eastward, once westward, while an identical clock sat still back home. When the traveling clocks landed and got compared against the one that never left, they drifted. Tens of nanoseconds. And the drift matched the pie budget math almost exactly. Motion had measurably spent a piece of those clocks' time. Want a version of this that happened to actual, living, breathing people? Look at astronaut Scott Kelly and his identical twin brother Mark. Scott spent nearly a year aboard the International Space Station, circling Earth at roughly 28,000 kilometers an hour. Mark stayed on the ground. When Scott finally came home, NASA compared the two of them, and among everything they measured was time itself. Scott came back younger than his twin, by a few milliseconds. Tiny, but not imaginary. Not some rounding error from bad instruments. Two identical twins, same DNA, same birthday, same childhood, spent different fractions of the same shared pie, and the universe kept the receipt. If Scott had spent decades up there instead of months, the gap wouldn't have stayed in milliseconds. It would have become something you could see in a mirror. Particle physicists lean on this constantly, because most of what they study barely survives long enough to be useful. Take a pion, an unstable particle produced in accelerators like the ones at CERN. Left alone, it decays in tens of nanoseconds, nowhere near enough time to cross more than a few meters. But accelerate that same pion close to the limit, and its internal clock, the one counting down to its own decay, slows right along with everything else we've talked about. It isn't living longer in any sense it would recognize. It's simply spending almost nothing on the time slice. So from our side of the fence, its decay stretches out far beyond what its rest lifetime alone would ever predict. Without that stretching, half the experiments at CERN wouldn't work. The particles would fall apart before they finished the racetrack. Engineers don't treat this as a curiosity. They design entire beamlines around it, betting real budgets on the fact that a fixed pie, sliced differently at high speed, will keep their particles alive long enough to be useful. Even your phone is proof of this, quietly, every single day. GPS satellites move fast enough that their onboard clocks run measurably slow compared to clocks on the ground, purely from speed alone. Left uncorrected, your location would drift by kilometers within 24 hours. So engineers deliberately build those clocks to run slightly fast before launch, so that once they're up there, burning through their own budget, they land on exactly the correct rate. Somewhere right now, an engineer's actual job is building a clock that's wrong on purpose, so the universe's real math can correct it back to right. Which finally brings us to light itself, and why it deserves almost none of the credit it's been given. Anything with mass, a rock, a spaceship, can never spend its whole pie on space. There's a hard rule baked into the math. Mass demands that some sliver of your budget always stays parked in the time slice. Somewhere, in principle, you have a place where you could sit perfectly still and simply age. That's called your rest frame. Everything with mass has one. Light doesn't. A photon carries no mass at all, and something with no mass has no rest frame anywhere in this universe. There's no version of reality where a photon just sits there. It isn't even allowed to keep a sliver of its budget parked in time, because that reservation only exists for things that have mass. So light's entire pie, every last percentage point, gets shoved into the space slice the instant it exists. It doesn't choose the speed limit. It has no other option. That's the whole answer. Not because light is special, because light is the one thing in this universe with nothing left to spend on time. And it flips something else that used to genuinely bother me. Why nothing with mass, no matter how much energy you throw at it, can ever be pushed all the way to that speed? It's not a matter of building a stronger engine. Reaching the limit would mean spending 100% of a budget that mass simply isn't allowed to fully spend. You can push a spaceship to 99%, 99.9, 99.99, and each extra decimal costs more energy than the last, forever, because you're chasing a finish line a massive object is structurally barred from ever crossing. Massless things don't win that race through effort. They were simply never entered in it. Follow that thread one more step, and it gets genuinely strange. A photon that left a star 10 billion light years away and just landed in your eye did not experience 10 billion years of travel. It has no time slice at all. Zero was spent. From light's own accounting. If that phrase even means anything, its birth and its arrival happened in the same instant. The entire 10 billion year journey collapsed to nothing. I want to be careful here, because this is exactly where people overstate it. A photon has no valid point of view to describe. No frame you could stand inside and look out from. What we can say honestly is that this is a limit. Push any massive object closer and closer to light speed, and both its travel time and the distance ahead of it shrink towards zero together. Light sits at the very end of that road, a destination the math points to clearly, one that nothing with mass is ever allowed to actually stand on. There's a deeper reason this speed limit exists at all, and it has nothing to do with things being fast. It has everything to do with keeping cause and effect in order. Picture any single event. A flash, a signal, a decision made right now. That event can only ever influence the parts of the universe a signal from it has had time to reach. After 1 second, everything within a light second. After a year, everything within a light year. Draw that expanding reach with time running upward, and it traces a cone. That cone is your future. It's the only part of the universe your event is allowed to ever touch. Now imagine something could beat the limit, could step outside that cone entirely. Here's where it gets dangerous. Different observers, moving at different speeds, disagree about which events count as at the same time. So a signal that broke the limit wouldn't just be fast for some of them. It would arrive before it was sent. Picture it concretely. You send a message to a friend on a ship pulling away from you, and suppose that message could somehow beat the budget. From your friend's point of view, moving through the same fixed pie at a different angle, their sense of now is tilted relative to yours. Run the math, and there exist observers, perfectly valid ones, for whom your friend's reply lands before you ever sent the question. Not delayed, not garbled, arriving first. Ask 100 different observers which event happened first, the question or the answer, and you'd get 100 different, equally correct answers. That's not a puzzle waiting to be solved. It's proof that the order of cause and effect would stop being a fact about the universe at all, replaced by something that shifted depending on who happened to be watching and how fast they happened to be moving. No universe built on that kind of foundation could hold together for long. The speed limit was never really protecting light. It's protecting the idea that causes come before their effects. And that's exactly why gravity, which has nothing to do with light, nothing to do with photons or electric fields at all, was clocked in 2017 traveling at that exact same speed. 2 neutron stars, 130 million light years away, collided and sent out 2 completely different messengers. A ripple in space itself, and a burst of light. They raced each other for 130 million years. They landed on Earth within about 2 seconds of each other. Gravity wasn't racing light that night. Both of them were simply obeying the same universal budget, because that budget was never about light to begin with. It belongs to space and time themselves. And anything without mass, whether it's built from photons or ripples in gravity, has no choice but to spend it all in one place. There's one more piece of evidence hiding in plain sight, buried inside the most famous equation in the world. E equals mc squared. Energy equals mass times the speed of light squared. Ask the question almost nobody asks. Why is the speed of light sitting inside an equation about mass and energy? 2 things that have nothing to do with light and aren't even moving? Look closely at what that equation actually describes. It's the energy something carries purely by existing, by having mass, while sitting perfectly still. There's no beam of light anywhere in that picture. The reason C shows up is the same reason it shows up in everything else we've covered. It's not light sneaking its way into a mass equation. It's the same conversion rate, doing the same job it's done all video, this time translating between mass and energy. 2 more things that turn out to be the same underlying quantity, viewed from a different angle. It gets squared because energy's units secretly carry a hidden distance and a hidden duration folded inside them. So the conversion has to run twice. Strip away our habit of measuring space in meters and time in seconds. Use the same currency for both, and the equation collapses down to something almost embarrassingly plain. Energy equals mass. Full stop. The speed of light only shows up because we never got around to fixing our rulers. And this is exactly why converting even a tiny amount of mass releases such a staggering amount of energy, with light nowhere in the reaction itself. Inside the sun, hydrogen nuclei fuse into helium, and the resulting helium weighs very slightly less than what went into it. That missing sliver of mass doesn't vanish. It converts, at the same fixed rate we've been tracking this entire video, into the sunlight warming your skin right now. A nuclear reactor runs the same trade in reverse, splitting heavy nuclei instead of fusing light ones. But the bookkeeping is identical. A whisper of missing mass, multiplied by that same universal rate, cashes out as an almost unbelievable amount of energy. None of it required light to be present. The conversion rate was simply doing its job, translating one unit into another. Energy is what mass looks like after the trade, and that trade has been running inside every star in the sky since before there was anyone around to name it after anything at all. So let's go back to where we started. A room, in 1983, where a group of scientists quietly stopped measuring the speed of light and started building their rulers out of it instead. That decision only makes sense once you see what the number actually was, all along. It was never a fact about a beam of light racing across a room. It was a fixed exchange rate, stitched into the structure of the universe itself, the rate at which space converts into time, and time converts into space, identical for every single observer, no matter how fast they happen to be moving. Ole Rømer clocked it with nothing but a moon and a stubborn refusal to call it error. He had no idea he was measuring anything bigger than one lonely coincidence in the sky. Maxwell stumbled onto the exact same number decades later, playing with bar magnets and charged plates. With no clue, he'd just connected it to a universal budget. Light was simply the first thing anyone ever caught spending its entire share on space. The fastest runner, in a race that was never really about running. And everything else in this universe, you included, is still holding on to a sliver of that same fixed pie, spending almost all of it on time, which is the only reason you're able to sit here and watch this sentence end before it began. The number we memorized as a fact about light was a fact about the room the whole time. Light was just the first tenant honest enough to show us the ceiling was there at all. If this changed the way you think about that number, subscribe, because next time we take this exact same budget and ask what happens when mass bends the room itself, and why falling is what it looks like when your slice of the pie gets pulled sideways. Rømer clocked it. Maxwell explained it. Next time, we bend it.